Hi, this is Mrs. Villette, and this is the Section 5.4 Notes video. Here, to start off with, we need to have an idea of what a periodic function is. So a periodic function is just a function that repeats its shape over a defined interval, which is called the period. So in this graph, our period is the length of this shape of the graph that repeats. We can write it in mathematics, f of x plus the period equals f at x, which basically just means if you transform the function f of x to the left or right p units, where p is the period, you will end up with the same function. So I can think about taking this section of the graph and just copying it and pasting it p units to the left, and I end up back on the function. So the period is just the amount of time it takes for the function to repeat an exact copy of itself. Now, there are some properties of the periodic functions that we're going to study in particular. We're going to look at sine, cosine, tangent, and the other reciprocal functions. We saw a little bit of this vocabulary already, but the amplitude is just the distance from the midline to the maximum or the minimum, and there is a shortcut formula for it. So first of all, we call the amplitude absolute value of A, and we'll see later why we need absolute value. And it is going to be the maximum value minus the minimum value divided by 2. So you're going to find the distance between the maximum and the minimum and half it, and that will give you the amplitude. The midline we will call y equals k. It's a horizontal line, and this is the average of the maximum and the minimum. So it's the maximum plus the minimum divided by 2. And then the period, there is a formula for it which we'll discuss later, but right now we just want to talk about it as the horizontal length required for the function to repeat. And for your reference, I've put the sine and, so we've got the sine and the cosine graphs here. And we can see that our sine graph has a period of 2 pi, and one period of the sine function starts at the midline, goes up to the maximum, back down to the midline, down to the minimum, and then back up to the maximum. And it takes that a length of 2 pi to do that. And you can see that that same exact picture is repeated over here over a length of 2 pi. We want to think about what the sine function looks like in particular as this first fundamental period where it goes midline, max, midline, min, midline. Then we've got the cosine function, and the cosine function has a similar shape except the cosine starts at its max. So it goes max, and then midline, minimum, midline, and then maximum. So a cosine period, a fundamental cosine period, starts at the maximum and ends at the maximum. And it still has a period of 2 pi, an amplitude of 1, and a midline of 0. So we're going to look at some transformations of these functions. The cosine graphs. Let's start off by graphing 2 sine of x. This number 2 in front corresponds to a vertical stretch, which on a sinusoidal function changes the amplitude. So let's start off with, just in black, I will do a regular sine function. So a regular sine function at 0 is 0, at pi over 2 it's 1, at pi it's 0, at 3 pi over 2 it's negative 1, and at 2 pi it is 0. So here's a fundamental period of the sine function. And our scaling is a little bit different, so this looks maybe a little squished than our previous sine function. So here's my sine of x. So 2 sine of x means we are going to stretch vertically by a factor of 2. Anything that's on the midline is going to stay on the midline because it has a y-coordinate of 0, and 0 times 2 is still 0. The maximum values is where we're going to see the big change. The maximum value of 1 will be doubled to 2, and the minimum value of negative 1 will be doubled to negative 2. So one period of this 2 sine of x looks like this. And then we just repeat this same shape, going midline, maximum, midline, minimum, midline, and we can even keep going in the opposite direction to kind of fill up the whole entire screen here. Now you want to try as best as possible to make sure that you have those nice smooth curves, that you're not doing V shapes, that you're doing something more rounded like we did on the activity. So this is y equals 2 sine of x. Okay, now let's do a transformation of cosine. Now our stretch factor is negative 0.5, so that does two things. It's going to compress the amplitude and flip it over. But again, I'm going to start with that fundamental period of cosine. Cosine normally starts at its maximum, then goes to its midline at pi over 2, its minimum of negative 1 at pi, then midline, and then back to maximum, all in 2 pi. When you start your cosine function, make sure you start at concave down, and then at the intercepts or the midline, switch to concave up, and then you switch to concave down again. And then we could keep on extending this. Let's round that one a little bit more there. Okay, we have a negative 0.5 cosine. Again, anything that's on the midline is going to stay. And then anything else is going to get half as big and reflected. So when I'm looking at this maximum value of 1, reflecting it would take it to negative 1, and then I would half that. So I would be at negative 0.5. And the same thing with the minimums. The minimums would change to maximums, but half as high. Okay, and then we could just keep extending this, following the pattern of just alternating between maximums to midlines to minimums and so on. And then this would be my y equals negative 0.5 cosine of x, and what we did in black at the beginning was just my y equals cosine of x. Now I've realized that I didn't do a particular example of changing the midline. So for midline changes, I encourage you to look at the activity that we did before, and the answer key for that is posted. So let's take a look at period changes. Period changes are going to happen on the inside with the x inside the sine function. And this is a Greek omega, so you're going to say a sine omega x. The thing we need to remember about horizontal changes is whatever they say, we actually do the opposite. So for example, when I say cosine of half x, that is actually going to be a horizontal stretch by a factor of 2. So this formula actually does that for you. The formula for the period, which we call t, is given by 2 pi divided by omega. 2 pi is the normal sine or cosine period, and then we divide it by omega. Instead of multiplying by omega, we divide, and that's kind of taking care of that, doing the opposite thing. So when I'm graphing this function, y equals cosine of half x, this half x, or this half, is going to correspond to a horizontal stretch by a factor of 2. It's going to be the reciprocal of 1/2. What that tells me is that my period is actually going to be 2 pi over 1/2, or 2 pi times 2 over 1, which is 4 pi. Now there's no change to the amplitude, so what I'm going to do is I'm going to go ahead and graph the regular cosine function for us, just for comparison. It starts at its maximum of 1, its minimum at pi is negative 1, halfway between those it's at its midline, it's at its maximum again at 2 pi, and then halfway at its midline. So this is my regular cosine function, just one fundamental period. Now what we need to do to this is stretch it out, and we always do the stretch relative to the y-axis. So this 2 pi is going to stretch by a factor of 2 to go all the way out to 4 pi. This pi is going to stretch by a factor of 2 to go out to 2 pi. Now this y-intercept is not going to change. That was stretching my maximums and minimums. The midlines are always going to happen halfway between those maximums and minimums. So right here at pi. And you can see that that corresponds to just doubling pi over 2. And then my other midline point is going to be at 3 pi, which corresponds to doubling 3 pi over 2. Remember, on a cosine to start concave down, then go concave up, and then concave down again. And what we can pay attention to is that 1/4 of the period is pi. So every time we do something kind of important on this graph, it's going to be a distance of pi. So moving to the left here, my next important point is going to be at negative pi. That's going to be a midline, and then a minimum, and then a midline, and then a maximum. So it really helps to work things in quarters. Those just correspond to the quadrantal angles, or the tops and sides of your circle. Now it's a little bit hard to actually think of this happening on a circle, because now it's taking 4 pi to fit one period, and that's just because we have this horizontal stretch factor that's actually changing the length of the period. So we can see that the length of the period on this, here's a fundamental cosine period, and that length is 2 times 2 pi, or 4 pi. Okay, let's look at an example of a sine function, and we're going to start by calculating the period. We have this 3, which should change the period, and it's going to actually be a horizontal compression by 1/3. If we just run this through the formula, t equals 2 pi over omega, we get 2 pi over 3. So the period is 2 pi over 3. Now I've purposely not scaled the x-axis here because I want you to think about how you want to scale it. I want to figure out quarter periods, because the quarter periods again are kind of hitting the quadrants around the circle. So a quarter of 2 pi over 3 is actually what I want my scale to be, which is 2 pi over 12, or pi over 6. If I want to fit at least one full period to the right of the x-axis, to the right of the y-axis, I need to scale by pi over 6's. So I'm going to make each one of these tick marks equal to pi over 6. So pi over 6 plus pi over 6 is 2 pi over 6, or pi over 3, and then 3 pi over 6, or pi over 2, and then 4 pi over 6, or 2 pi over 3. And see, that landed me nice and perfect on the end of the length of the period, which we decided was 2 pi. So here's going to be the end of my period. Now, I'm going to go ahead and try to do this without graphing the parent function, which is the sine function. I know that a sine function normally starts on the midline, and it reaches its maximum point at the very next quarter of a period. So this corresponds to going quarter of the way around the circle. The maximum value is going to be the amplitude, which is 3, which is actually right at the tippy top of my graph here. And then it goes back down to the midline. 3/4 of the way through, it reaches its minimum, and then all the way through the period, it's back at the midline. We're going to try to make this nice and smooth. There's one period, and then we can do a second one, just realizing that as I go backwards, it's like starting at the end at 2 pi over 3 here. I'm going to go back to the minimum, then to the midline, maximum, midline again. And there is our transformation of our function. Now, just for fun, let's go ahead and identify that the absolute value of A is the amplitude, which is 3. So that's my amplitude. My period is 2 pi over 3. And so far, we haven't done anything with changing the midline, so y equals 0 is the midline. So that should get you going on your homework, and hopefully also help you with your formal homework. The formal homework is a little bit different because it does have a midline, but I think you will be able to figure that out. And when you're trying to figure that out, make sure you look at the page where I gave you the shortcut formulas for how to find the amplitude and how to find the midline.